Hi all, thank you so much for starting to watching this video. Today I'd like to start analog layout design tutorials. As part of that analog layout design tutorials, I'd like to begin with analog VLSI design because analog layout is extensively used in analog VLSI design. So let's begin. So before going any further, what is analog? So everything around us is analog. So like temperature, audio, voltage. These are all real world continuous signals. Whatever real world continuous signals we have, so that is all analog. Okay. And it bridges the gap between physical world and digital systems. Okay. And it does by using sensors, microphones, antennas, and it generates analog signals and that must be processed before digital conversion. So right now I'm speaking through microphone. My speech is converted to electrical signal using a microphone and we are able to use Wi-Fi because of antennas. So these are all analog signals. They are converted to electrical signals using some sensors and some actuators and that is converted to analog electrical signal that is processed for using digital conversion. Okay, so it is very critical in low power and high precision applications such as medical devices, IoT, RF front ends, audio circuits, and power management. Okay, so this is all about analog, and VLSI refers to integrating thousands and thousands to millions of transistors on a single silicon chip. Okay, so what exactly we do in analog IC design is designing an amplifiers. So amplifiers are that can be used to convert a low amplified signal, low amplitude signal to high amplitude. Let's say this is our low amplitude signal. It can be converted to high amplitude. Okay. So there are various amplifiers, so such as op amps, transimpedance amplifier, and there is a filter. So these filters can be active and passive filters to allow to or to block frequency components, and there are voltage and current references. So these are on chip. Okay, so these are on chip voltage and current references, so such as band gap reference, current mirror, biasing circuits, and we require to generate a stable clocks. So this can be done by oscillators, phase lock loops, and we need to convert our analog data to digital data and digital data to analog data. So that can be achieved by our data converters. So the technology behind all of this analog IC design is CMOS. So there are various other technologies as well, but CMOS is the predominant. Okay, so let's look at CMOS technology with an example of inverter. So we can see here, yeah, we can see a inverter schematic here. Okay, so it is built using PMOS and NMOS devices. Okay, okay. So I hope you are all aware of PMOS and NMOS. So this CMOS technology is abbreviated as complementary metal oxide semiconductor. Okay. So before moving any further, let's discuss about briefly about MOS devices, and then we will come back to our discussion on CMOS. Okay. So MOS is metal oxide semiconductor. Okay. So in that NMOS and PMOS. So the metal oxide semiconductor transistor. Okay. So this is built by using uh, metal and oxide and semiconductor. So this is our metal oxide semiconductor. So because of this structure, it is called as metal oxide semiconductor. And NMOS and PMOS are defined based on the carriers, carriers of current flow. Okay. And the symbol of NMOS is, so let's talk about NMOS. The symbol of NMOS is it has four terminals. So this is drain, source, gate, and bulb. So you might not have seen bulk terminal, but bulk is very important because through that only we will be able to build our transistor. So if you look at the layout view of NMOS, so it is built by using two NMOS diffusion layers and our structure, the oxide, the gate, this is our gate, this is our SiO2, SiO2, this is our source and drain. And it is built in a P substrate. Okay. And why it is called NMOS? Because if there is a current flow between drain to source, so if there is a current flow between drain to source, then the transistor is on. So that's why, and the carriers are electrons. And in a P substrate, the majority are holes. Okay. And because of this flow, this is called as this carrier flow, this is called as NMOS. Okay. So meanwhile, similarly, for PMOS, it's vice versa. That is, so here also we have four terminals, bulk, source, drain, and gate. Okay. And it is built with two P plus regions, and we all know this is SiO2 and this is our gate. Okay. So The in MOS, so in older technologies, the metal used was aluminum, but now in order to be compliant with the silicon process, this metal is a polysilicon and oxide. Oxide is oxide is O for oxide, that is SiO2, and S is semiconductor. So this is based on whether it is PMOS or NMOS. In case of PMOS, it is N-well. In case of NMOS, it is P sub. Okay. So now we want to realize both NMOS and PMOS in a single substrate. By the way, this is also called as substrate or bulk. Okay. So that we need to realize in a single substrate. That is generally accomplished by using taking a global substrate. So this global substrate is generally P substrate. Okay. And how do we generate PMOS? The PMOS is generated using a by digging a N well. So this is our N well and this is our P sub. Okay. And here, so we built this N plus diffusion for NMOS, P plus diffusion for PMOS, and then gate, sorry, so oxide, then oxide and gate. Okay, so yeah, this is our gate, and this is our source, drain, source. So in mass structures, both source and drain are interchangeable. This may not be possible in BJT because because in a BJT, base, collector, emitter, both of them will have different, sorry, all of them will have different areas. Okay, so typically, so I'm just giving a brief of it. So the emitter, base, and collector. Collector will have more area compared to emitter. That's why we cannot interchange terminal in BJT, but it is possible in mass structures. Okay, and yeah, this is the introduction to it. So let's come back to our inverter example. So what we can do is we can, so now we have built our both PMOS and NMOS in our PMOS and NMOS in a single substrate. So let's connect them. So you can see, so let's build our schematic. So this is connected to VDD, and this gate, both of the gates are connected, and this is our AB. So let me make it V out. Okay. So now we have built our P sub and N well. So and we will connect it with the using a metal one. Okay. And these two terminals needs to be connected. So either we can connect it using other metal, or we can directly draw poly layer. So I'm using a poly layer. I'm using a poly layer to connect. Okay. Yes. And this is connected to ground. This is connected to VDD. Okay. So let's come back to our presentation. So you can see here, this is our NMOS transistor, and this is our PMOS transistor built in a NVL. And you can see both drains are connected. Both drains are connected using a metal one. So you can see here. So the metal one is connected with the drain of NMOS and drain of PMOS. And this P plus diffusion and N plus diffusion are for P PMOS and NMOS. This is SI vertical layer, that is our oxide layer. So this is built in a single substrate. So this is how typical CMOS technology looks like, where we can build both NMOS and PMOS. So in a VLSI design ecosystem, we have various design companies where they do the design. So like Qualcomm, Intel, Samsung, and we have foundries. So these are fabs. So there, our designs are manufactured. So TSMC, ST, and they give PDK to both the designers and the EDA companies. And using that PDK, we will build our design and we generate a GDS that is sent to the foundry. Foundry will make a chip and give it to us to test. Okay. So this is how a typical VLSI design ecosystem looks like, and these are the prospective employers. Okay. And after this video, I'd like to give introduction to analog design and various CMOS devices, passive devices, layout and their rules, and floor planning and placement techniques, parasitic aware layout and layout dependent effects, guarding and shielding, analog IP block development. So I'll pick any layout, so any op-amp or VCO. So we can dig deeper into understand whatever the techniques we have learned in the prior videos. Okay, thank you so much.